So today we're talking about continuity in behavior and limits. It shouldn't take us too long. You guys have a chance to start on your homework. But no, students will be able to use limits to determine continuity of a function, apply the intermediate value theorem, and describe in behavior. Now, more than likely you guys have described in behavior before, back in algebra 2. The one thing you probably have not done is use limit notation to describe in behavior, or use that to determine whether or not a function is continuous or not. So this is like your little list of some things that you will use very often once you get to calculus. Okay? You will be using limits a lot when you get to calculus. IB, it's like you'll use it, but not as much as you would use it like in a regular calculus class. Okay? So, graphs. A graph of a continuous function has no breaks, no holes, or gaps. You can trace the graph of a continuous function without lifting your pencil. That's how you know if it's continuous or not. Right now, off the top of your head, can anybody tell me a function that is not continuous that you know of? Off the top of your head. Reciprocal functions. Because don't I have to lift up my pencil to get to the other piece? That's one. Anybody else? Raised integer. And I heard piecewise functions. Yes, all those are examples of functions that are not continuous. At some point in time, I'm going to probably have to lift up my pencil to get to the next part of it. Now, the concept of approaching a value without necessarily ever reaching it is called the limit. Okay? So I will refer to as, instead of saying the closer we get to x, or the closer we get to infinity, I might say the limit as x approaches infinity. They all mean the same. Okay? Now, you can have three types of discontinuity. In other words, functions that are not continuous. That's what discontinuity means. Functions that are not continuous. You can have infinite discontinuity, which are like your vertical asymptotes. You can have jump discontinuity, which are your gaps in your graph. Or you have removable discontinuity, also known as point discontinuity, which are your holes. Yes. How you doing? Yeah. All right. So those are your three types of discontinuity. Okay. So out of the ones that we said reciprocal, we said greatest integer, and we said piecewise. Infinite discontinuity. Which one of those three has infinite discontinuity? Say it again a little louder. Reciprocal. Doesn't a reciprocal function have a vertical asymptote? Right there at the y-axis. What about jump discontinuity? Greatest integer, that's for sure, because I have to go up to the next step. I have to jump up there. There's a gap. Oh, and also what? A little louder. Piecewise. Yes. Okay? Now, removable discontinuity, those are actually and some of your reciprocal functions, and also have removable discontinuity. It just depends on what type of function you have, but you'll see it in just a second. Now, infinite and jump discontinuities are classified as non-removable discontinuities. Okay? A non-removable discontinuity cannot be eliminated by redefining the function at a particular point. So in other words,
you don't have the black hole and the white hole?
Yeah. That's what it basically. A function is continuous at x equals c, c being some constant, if it satisfies the given conditions. The only way that something is continuous is if it hits these three conditions. The first, f of x is defined as c, or in other words, f of c exists. That means if you have a function and they give you a c, say 2, and you plug it in and you get a number, then that means f of c exists. Okay? So you're plugging in a number into your function. Now, number 2, f of x approaches the same function value to the left and to the right of c. So in other words, the limit as x approaches c of your function exists. So if you look, So if you look at a particular function, when it means approaches the same function value to the left and to the right, okay? What kind of function is this? It's quadratic, okay? And let's say that this right here is 2. If it approaches from the left and from the right, that literally means as I'm going along your curve from the left, it's approaching a value, and then if I go along your curve from the right, it approaches a value. Does everybody see that? What I mean from the left and from the right? Like you're coming from the right, from the left. And it's approaching a particular value. Okay? It actually exists. Like there's no hole, there's no gap, nothing. Alright? Lastly, the function value that f of x approaches from each side of C is f of C. So in other words, if I'm approaching from the left and the right, whatever that number is the same number I got when I evaluated the function at C. That's how you know a function is continuous or not. It has to fit all three of those. Okay? So the first, f of C has to exist, meaning it has to be defined. If you're approaching from the left and the right, it actually approaches a number. And the last one, if whatever number it approaches is the exact same thing you get when you evaluate. Okay? Now, question. So here's our example. We're going to determine whether or not the function is continuous at the given value. We're going to justify our answer, so we're going to show a little bit of work. And if it is discontinuous, we're going to identify what type. Okay? F of x. What kind of function is this? The piecewise function. Now, we graphed piecewise functions. We've seen a couple piecewise functions, haven't we? More than likely, there might be some gaps. Okay? Because it's divided up into two pieces. That's how we know. Because you have two functions that only define greater than a particular number and less than a particular number. So, let's see if it is continuous. The first continuity test, you can call it, is to see if f of C, C is 2, that's what they give us, actually exists. Now, you guys know how to do this. We did this back in lesson 1. 2, we're going to plug it into my function. Which piece of my function am I going to plug it into? Into the x, but more specifically the second one. Because as you see, x is equal to 2 for the second function. So what is f of 2?
1.
It exists, right? 1's a real number. So far, so good.
So what number were you guys at?
Something that wouldn't exist, say you had a reciprocal function, and the number you plugged in made it 0 in the bottom. Think about it, 1 over 0 is undefined, right? That would be an example of where it doesn't exist. Okay, hear that? The next one, we have to see if the limit as x approaches C from the left and from the right actually exists. So how do you distinguish between the left and the right? Minus means the left. Positive means the right. Okay? That's how you'll be able to distinguish. Now, let's figure this out. This is a piecewise function. And 2 just happens to be the point where the interval makes this break. Coming from the left, what's to the left of 2? What numbers are to the left of 2?
1,
1, 0, -1, and -2, and so on and so forth. Do those numbers, are those less than or equal to 2 or greater than 2? Less than or equal to 2. So when we're coming from the left-hand side of the function, we're only looking at this part of the piecewise function. Does everybody understand that?
No.
Okay. If I were to graph this piecewise function, let's graph it real quick. A good review from Friday's lesson. So here's your piecewise function. If I'm approaching from the left, I'm basically coming up this way along my graph. Does everybody see that? Okay? Approaching from the left. I'm coming up this way. So I'm on the x minus 1 part of this piecewise function. What number am I approaching? What y value am I getting close to? I'm getting closer to, you're right, 1. You can also get that by plugging in 2 into the second piece of the piecewise function. Based off of the graph, like basically we're trying to figure out what are the y's getting closer to as x is closer to 2. That's what we're looking at. Okay? Question? No. Because look what happens when you look from the right. By coming from the right, going down this way, what number am I getting closer to? What are my y values getting closer to? 4. I can also figure that out by plugging in 2. Are you sure it's 4? My graph might be a little bit off. It's 5. You can also figure this out by plugging in 2 into the first equation in the piecewise function. Now, they both approach a number. They both exist. So requirement number 2 fits. Now requirement number 3 basically says that these numbers right here in step 2 have to equal the number in step 1. But they don't. So because the limit as x approaches 2 from the left and the right do not equal the number you get when you plug in 2 into the function, this is not continuous. It's only a lot of work now because it's the first time you're dealing with it. But the more practice you get, you'll be able to recognize that, hey, quick enough. Trust me. Not all piecewise will be discontinuous. So you've always got to check step 2. At different points, yeah. What kind of discontinuity do we have? You have a jump discontinuity. You have a jump discontinuity. Okay? You gotta make sure you write that in there because for whatever reason my pen is not registering in certain places. How do you know? Oh, calibrate it? I will in a second. How do you know it's jump discontinuity? It's not infinite because we don't have any vertical asymptotes. The reason why we don't have any vertical asymptotes is because we do not have any denominators that we have to set equal to 0. We know it's not removable discontinuity because of the fact that we don't have any fraction reciprocal type of functions. We're just dealing with like linear quadratics and so on. So, okay? Let's look at B. Okay? Now, knowing what these functions look like can really help you out. We knew number 1 was a piecewise function. What's number 2? What's B? A quadratic. Now think, is there any point where a quadratic could not be undefined? No. Okay? So using that can kind of help us out a little bit when it comes to figuring out if this is continuous or not. You're finding f of c. What is c in this problem? 4. Now I have to clear this off. Does everyone get this down? So c is 4. So when we plug that in, we get that f of 4 equals 39. Okay? And that's a number. It's not, 39 over 0 or something is the actual number. So now we look at the limit as x approaches 4 from the left and the limit as x approaches 4 from the right. You could solve it algebraically. Might be a little time consuming. You might have to use your calculator a little bit. But this is a parabola. Looks like a U, correct? No matter what, whether you're approaching it from the left or approaching it from the right, aren't you going to approach the same number? No matter what? Okay? If you don't believe me, look at your calculator. I see some of you guys have a calculator, not everybody. Look at your calculator. That's not it. It was x squared
Plus 5x plus 3.
Okay, I can't see formulas. But press second graph. And hopefully yours is not like mine. Press second table. Second window. Press second window. Does yours look like mine? Is both autos highlighted? Do you start at 0? If you don't, go up to it, click 0. Make sure it goes by ones if yours is not like this.
Wait, so where do we have to hit second graph?
Hit second window
Second window.
first. Make sure it looks like this.
And then we're good.
Hit second graph. Your first number was 0. Look at your table. Go further down. Get closer to 4. Okay? Press the second graph now. Okay? Now, the closer you get to 4, what's happening with your y's? What numbers are getting closer to? If you look at 3 and you look at 5, what are those two numbers when you look at your table? You got 27 and what? And 50. 53. Just 53? Okay. Change it up. Go back to second window. Make your table start at 4. Make your change in your table be 0.1. Now go back to second graph. Look what happens to close. Oh, so now it won't work. I don't know why it didn't work this time. So now look what happens. As I'm approaching from the left, that means I'm getting closer to 4 from the left. What number am I getting closer to? Look what happens when I'm approaching from the right. What number am I getting closer to? So as I'm approaching from the left, I'm getting closer to 39. As I'm approaching from the right, I'm getting closer to 39. Does the limit as x approaches 4 equal the same thing as f of c? So that means this function is continuous. We could also know that because this is what kind of a picture now? It's a quadratic. Someone is asking questions. Say it again.
You could have just done that in 3 seconds. You didn't just go through it. Like on homework.
Yes, now with quadratics, yes, you will know that they are continuous. However, you do need to make sure that you check, because not every piecewise function is going to be discontinuous, and not every linear function is going to be continuous. You got to be careful, okay? So you do need to make sure you check every time, okay? Questions? Yes? If it has a hole. The graph may show up to be linear, but there might be a hole somewhere along that line. They could give you an equation that when you do work with it, like you do f of c, you plug in any number, it might give you a linear function at the end after you simplify, and then your graph will look like a line. Your simplified function will be a line, but then there's a hole there. You'll see one like that in your homework. If a function is continuous, you can approximate the location of the zeros by using the intermediate value theorem, and it's called the location principle. The intermediate value theorem says the following: if f of x is continuous and a is less than b, a and b being some numbers on your graph, on your x-axis, and there is a value n such that n is between f of a and f of b, when there is a number c such that a is less than c, which is less than b, and f of c equals n. I'll give you guys a second to write that down, and I will break it down piece by piece. So, breaking it down piece by piece. If f of x is a continuous function, we just talked about what a continuous function is, right? Okay. And a is less than b. Okay, so if you look at this graph, say a is 2 and b is 8. Alright? Then there's a value n such that n is between f of a and f of b. Okay, so I know you might not be able to see it that well. Go ahead and put it in right here. Okay? So there's a value that's in between f of a and f of b. What does f of anything mean? What's f? It means y. So when a is 2, f of 2 is the corresponding y. When b is 8, f of b is the corresponding y when x is 8. So there's some number that's in between these two y values that exists when you have a number c that's in between them. This is the intermediate value theorem, which ties along into your location principle, which basically tells you this: that if f of a and f of b, if they have opposite signs, if one's a positive and one is a negative, then there is at least one value c. You know, a is in between, c is in between a and b, where f of c equals 0. So that means that between those two y values, there is a point where y equals 0. When y equals 0, what does that mean? On a graph, when y equals 0, careful, other one.
Oh, okay.
There's an x-intercept. So if you have a function that is continuous, they give you an interval. And from f of a and f of b, if they change signs, that means there is a 0 that exists between those two x values. That is what the intermediate value theorem tells you. As garden variety as I can give you. Okay? If you have a function, and they give you an interval, and the y value for one of the endpoints and the y value for the other endpoint, if they're different signs, then that means there is an x-intercept somewhere between a and b. Question? Like one's a positive, one's a negative. So like the y value is like positive 4 and the other y value is like negative 2. Yeah, this probably wasn't the best way to do it. I see what you're saying.
What? I just think that's it.
Okay. Do me a favor, right beside this picture, draw this picture. Okay? Do me a favor, right beside this picture, draw this picture. So I'm going to try my best to make sure you guys can understand this, can see this, okay? A and B represent your intervals. Okay? You have some function f of x, and A and B are the intervals of the curve that you're looking from A to B, start to finish. Now, in between A and B, doesn't it cross the x-axis? Yes, it does. Okay? That point is going to be labeled C. Okay? C represents some x value where there's an x-intercept. Okay? Now look at f of A. Look at f of B. This might be easier for you guys to see. Okay? In this particular example, f of A is a positive number, yes? F of B is a negative number, yes? So by the location principle, which backs the intermediate value theorem, says that if they change signs, there's an x-intercept somewhere between the value of A and the value of B. Wouldn't you agree? And that point is whatever C is. Okay? Yes? There's somewhere in between them, there is an x-intercept.
It seems really obvious for that. Yeah.
Let's look at this example that applies that theorem. Okay? We're trying to figure out where, in between what consecutive integers, consecutive meaning what? Consecutive meaning what? What does consecutive mean? In order. One right after the other. Where there are some zeros here. And we're looking between intervals -4 to 4. Now we're looking at the integers. What integers lie between -4 and 4? 3, -3, -2, 1, -1, and 0. These are all your integers that lie between -4 and 4. I want to plug in these numbers into this function. Wherever they change signs, what happens?
There's C.
There's a C, which represents what? An x-intercept. Okay? Okay, so to finish off this video, because I got cut off by the bell, we are basically trying to plug in these consecutive integers between -4 and 4 included to determine where the real zeros exist, okay? So we're going to plug in -4, -3, and all these other x values into the function for x, okay? So that way we can figure out if they change signs or not. Because as we recall, if the y values are changing signs, then we know that there's going to be an x-intercept, okay? So here we go. When we plug in -4, we are going to get our value. All right, so when we plug in -4, we're going to get -46. We're going to get -13. And as you see, I use my calculator here to figure out these values, okay? It's kind of a way to cheat. Basically, I type my function into y equals, and then I went to my table to see that, hey, here are all my values. -2 is 2, -1 is 5, 0 is 2, -1 is, or 1 is -1.
Good afternoon, Highlanders. Just a reminder, you should only.
And then we see that we have 2, 17, and 50. Okay? Now, right here, we see that we change signs from negative to positive. So that means between -3 and -2, there is a y-intercept. We also see right here that it changes signs again. So between 0 and 1, there is an x-intercept, and we also see right here that between 1 and 2, it changes signs. So that means that there are x-intercepts between -3 and -2, 0 and 1, and 1 and 2. And what you can confirm by looking at the graph is that we see right there between -3 and -2, between 0 and 1, and between 1 and 2, it does cross the x-axis. But whether or not we had a calculator or we didn't have a calculator, we could figure that out again by using the intermediate value theorem. The last little bit is in behavior. And in behavior of a function describes how the function behaves at either the end of the graph or basically what happens to the value of f of x as x increases or decreases without bound. This again uses limit notation right here to represent, that as the limit as x approaches negative infinity of the function, that basically means left in behavior. So what's happening as x becomes more and more negative? For the second one, it's asking for right in behavior. As x becomes more and more positive, we're trying to figure out the limit as x approaches positive infinity. Now, your f of x values may approach negative infinity, positive infinity, or a specific value. You have to be able to look at the graph and determine that. So, we're going to use the graph to describe the end behavior, and we're going to use limit notation to do so. So here, if we look at the left end behavior, okay, as x gets more and more negative, we see that it's going to continue to go down into my negative infinities. So the limit as x approaches negative infinity of our function is going to indeed equal negative infinity because it's continuing to get bigger and bigger in the negative direction. Now if I look at the right end behavior, again, as x gets bigger and bigger and bigger, my y's are also getting basically smaller. They're getting closer to negative infinity. So as the limit as f of x approaches positive infinity, of the function, then I'm approaching negative infinity as well. And that's how you describe end behavior using limit notation. Over here for the next one, we see as x approaches negative infinity, okay? It looks like it's leveling out here because, again, this is a reciprocal type of a function. And we see that it's actually going to be leveling out at the number 5, okay? So the limit as x approaches negative infinity of our function is going to equal 5. And we also see on the other end, as the limit as x approaches positive infinity of our function, it is going to approach 5 as well. Now, if you're wondering, will it always be the same? Will the limit as you approach negative infinity and positive infinity always be the same? No. No, it won't be, okay? And so you do have to be very cautious of the way the graph looks. You could also type these functions into your calculator and look at the graph, look at the table, and see that as x gets bigger and bigger in either the positive direction or in the negative direction, what number it actually indeed is approaching, okay? Now, what I will also do for you guys, I will post this video up. If you're watching up to this point, you'll see that you've watched this video already. But not only that, I will also put up videos of other people explaining continuity and the intermediate value theorem in hopes that it makes a little bit better sense, okay? Because honestly, I feel like today some of you guys probably left confused, and I definitely don't want that to be the case, okay? So take a look at the other videos that I'll post, and please bring your questions for class tomorrow.